I'm gonna record this session. I was saying that I recommended, or part of the things that you need to do is to complete this. You have to watch the video. This video takes you step by step. I'm gonna do it also. I did it yesterday, before yesterday, how to fill out this table. I have a Mac, and sometimes what you do in Macs is not the same of what you do with the other. So so my point is, I think here is better. So the whole point is that we need to, so you need to watch the video and then be ready to do this. It's very easy, and you're gonna get good ideas on how to understand these conditional probabilities. We're gonna be using probability from now on. So it's very important that you understand this process, okay? So, okay, let me put this on the side. So last time we were working on some issues, and I'm gonna just go back to, so we cover many issues, many of the language that we need to use, the concept of probability, which is basically the relative frequency of an event. So the number of outcomes of event A, for this case, divided by the total outcomes in the sample space. Once again, that's what we did, frequency divided by the sample size. So so that's basically the most accurate definition for the empirical. So that's when we are doing exercises and we are measuring in real life the event as is occurring. So we also say that the more we try this experiment empirically with having a big sample size, so it's very likely that this empirical probability in the long run is going to become the classical or theoretical probability. So that's very important. And we mentioned this law of large numbers, which is very important. We also mentioned the fact that we're going to be dealing with two types of events, those who are mutually exclusive or not mutually exclusive, and those who are called the independent or dependent events. So, so we were advancing on all these issues. We mentioned the idea of conditional probability. So this is the conditional probability taking into account our sample space and the fact that we have two different events, A and B, and I am asking for the probability that A happens given that B has already occurred, right? So in this case, the probability that A happens given that B has already occurred. So in this case, B already, I know is an even number. So an A is phasor 2 and 3. So I want to compute that particular probability. We explained that before. We also use a table. So in this case, a 2x2 table, we can expand this, but this is 2 rows, two columns. We can do this with 20 rows, 20 columns, and the effect is going to be exactly the same. So in this case, we were looking at the present that the child has high IQ, given that he has the gene. So among all the people who have the gene, that's what happened, that this is A. So we are looking for those who have a high IQ. So if the question is, the child has a gene, given that the child has an IQ, a high IQ, so that is going to be reversed. So it's going to be the probability of A given B. So that is going to be the opposite. And remember, in this case, we accounted for the presence of the gene, and B was the high IQ. So in this case, now the gene is what so the child has the gene, given that the person has a high IQ. So in this case, we're going to use the 33, and it's going to be now divided by 52. So the probability of A given B is going to be the probability of having the gene given that the person has a high IQ. So this is going to be computed as 33 divided by 52. Okay, so those conditional probabilities, as I said, are not difficult to compute, but at some point they require that you focus your attention in which one is A, which one is B, and how this is going to work, right? If this is the probability of B given A, so, and I know that B is going to be the gene, sorry, B is going to be the high IQ, and B is going to be the gene present, so I can figure this out in this way, okay? So it's a matter of just paying attention to how understand these arrangements, okay? So we talk about the independent events. We say that when the conditional probability of A given B is equal to the probability of A, or the conditional probability of B given A is equal to B. So that means that these two events are independent. In many cases, you can notice that the two events are independent because they cannot occur at the same time, right? So, or the fact that one doesn't affect the other. So in this case, we had some examples, and we say that in order to find the probability of A and B happening in sequence is going to be the probability of A times the probability of B. So this is very important because we also have cases where the events are not dependent. So in this case, the probability of A and B are going to be measured by the probability of A times the probability of B given that A has already occurred, right? So we're going to see some cases at the end. So we saw some examples. So this is an example for an event that is dependent. So we can see that the probability of B, that B is a queen, so it's 4/52. But the probability of B given that A has already occurred, and assuming that the card has not been replaced, so now we have 4/51 because we already withdrew a card, and that card happened to be a king. So now the probability of a queen is changing because we have 4/51, right? So we still have 4 queens in the cards, but now we have only 51 in the deck. So, so we have this also. This is an independent event, very clearly, tossing a coin and getting a head. So, so so this hand should be here. So then rolling a six side die and obtaining a 6. So, so I think I erased something here. Tossing a coin and getting a head A, then rolling as, okay, then rolling as 6 died, 6 side died and obtaining a 6. So the first event is a head and the second is a 6. So if you are rolling a die and tossing a coin, of course, those are 2 independent events. Tossing a coin doesn't affect what happens with the die. So we are gonna see that the probability of this is 1/6 because this rolling a 6 has nothing to do with the coin. So so that is the conditional probability, but also the real probability of this event is going to be 1/6. So because these two are equal, these two, so going back to our equations, so the conditional probability has to be equal to the probability of the event. So in this case, we can see that probability, the conditional probability and the probability of the event are exactly the same. We can say that those events are independent. So a better way to understand the dependency and independency, first of all, as I mentioned before, we are going to look in our statements the word and. So when you see the probability of K and Q, so that means the probability that K and Q happen in sequence. So what is that probability? That I have one event and this event is going to affect the next one or is not going to affect the next one. So in this case, it's very clear that because the card is not replaced, we have a dependent event. We can compute the conditional, the probability of A and B, of K and Q happening in sequence by using the so-called multiplication rule. So we mentioned that before, I guess, no? Yeah, so in this case, this is the multiplication rule. We specify the multiplication rule a little bit more at the end after this. So in this case, the probability of K and Q happening in sequence, we know that this is a dependent event. Therefore, we have to use the probability of A times the probability of B, given that A has already happened. So in this case, A is going to be the king that has been already withdrew from the deck, and Q is B. So in this case, this is probability of A times the probability of B, given that A has already occurred. So we have to think on those terms in order to organize the information. Otherwise, you might get some wrong results. So we also have this case computing the multiplication rule for independent events. So we are using the multiplication, multiplying the probability of A times the probability of B. So in this case, A happens to be a head and B happens to be a 6. So the probability that A, H, and 6 happen in sequence because they are independent is just the multiplication of the associated probabilities. So we have this replacement and not replacement. So very likely with replacement, we are going to have dependence or not independent events. Very likely with replacement, we are going to have these independent events. So I was mentioning that here. So what happens if the card is replaced? So all the probabilities are going to be exactly the same because the card is going to be replaced over and over. So, so that's what this slide wants to say. So we have the multiplication rule. This is more clear. We can see the probability of A and B happening in sequence is going to be the probability of A times the probability of B, given that A has already occurred. So, and for independent events, it's going to be the probability of A and B equal to the multiplication of these two probabilities. And we mentioned that this can be extended. When we have independent events, we can multiply those events and get the result. So as happens in this case, we have 3 surgeries. Each surgery has an 85% probability. So we multiply these percentages 3 times to obtain the probability that the 3 surgeries in a sequence are going to be successful. So we also computed the opposite, the probability that none of them is going to be successful. So if this is the probability of success, this is by definition of the complement, we are using the 1 minus 85 to find the complement. So this is the probability of failure. If we multiply the probability of failure for the 3 surgeries, we have a 0.3%. So we also mentioned that by using the idea of the principle of the complement, we can find the probability that at least one of these 3 knee surgeries is successful. So if we have non-successful and we have at least one, so we are going to have a 99.7%. So if you were working in a well, as I said before, statistics are good for everybody because you can say stories about what you want to defend. So in this case, if you are a pharmaceutical company and you want to defend, or you are the hospital, right? So you can say, look, based on my data, we the probability that at least one successful surgery is going to be 99%. So that's very high. If you were a lawyer, you will be using some different things, right? So that's what they do when they have these lawsuits. Basically, most of the information that they collect is based on probabilities of success and failure. So that was another example. In this case, we have a case where there are more than 15,000 students applying to medical school. 93 of them were accepted, 82 of the 93, so that's the condition, that out of the 93, 82 of them were matched with resident positions. So what is the probability that, in this case, the question is, find the probability that a randomly selected senior was matched with a residency position and it was one of the 3 top choices. So these 82% are people who were placed in one of the 3 top choices. So we have A, the match with residency position. B is the match with one of the 3 top choices, given that they have been matched with the residency. So the probability of A is going to be 93%, 0.93. The probability of B, given that they has already occurred, is 82. So we have the probability that A and B are happening in sequence is going to be, once again, the probability of A times the probability, the conditional probability of B, given that A has already occurred. I was kind of lazy. I didn't multiply this thing. So this is 0.93 times 0.82. So the result is 0.7063. Okay. So or this is equal to the 76.3%. Right. So so moving on. So we also have the, so using the complement, find the probability that a randomly selected senior who was matched with a residency position did not get matched with the top 3 choices. So we know that 82% of them, they were matched among the 3 top choices. So the complement for this, so as we can see, the complement of the conditional is going to be 1 minus the probability, the conditional probability. So 18% of the people did not, so were matched to another school. So besides the independent events, we also have what is called mutually exclusive events. So A and B are mutually exclusive if they cannot occur at the same time. This means that A and B do not share any outcomes, and the intersection of A and B is going to be equal to 0. Okay, so that means that, so in this case, we have mutually exclusive events. So A and B don't share any of the elements. However, A and B here are sharing some of the elements, right? So those are not mutually exclusive. When this happens, when there are elements in common in the 2 different diagrams, Venn diagrams, so that means that, so they are not mutually exclusive. So we have a very simple example, roll a 3 on a die, roll a 4 on a die. So those are mutually exclusive because when you roll the die and it's a 3, it cannot be other different numbers. So those numbers are unique. So these outcomes cannot occur at the same time. I mean, unless this is a very weird die, but we are thinking about a fair die. So decide if the events are mutually exclusive. We mentioned this, randomly selecting a male student and randomly selecting a nursing student. So as many students at Lehman are males, and many of the nursing students are also males. So that is a non-mutually exclusive. So the student can be a male nursing major. So, so the addition rule is very similar to the previous one. So the probability that A or, so remember in the previous, in the multiplication rule, we were using and. So in this case, which rule do you need to apply? Well, I need to see the proposition. In this case, is the probability of A or B, right? So when they are not mutually exclusive, so we are going to have the probability of A plus the probability of B minus the probability of A and B. Notice that this is the probability of A and B. In the previous one, we were looking at the conditional probability, right? So that the multiplication use the conditional probability, whereas the addition rule uses the intersection of both, right? So sorry, uses the union of both. So so when I mentioned here, so this is not the intersection, it's union. So so we are gonna see that in our Venn diagrams. So in this case, to summarize this, the addition rule for not mutually exclusive events is going to be the probability of A plus the probability of B, and the probability of A and B are happening in sequence. So for the mutually exclusive events here, the rule can be simplified. When they are not, when they are mutually exclusive, I just add the two different probabilities, and that can be expanded to more cases. In this case, I just can deal with A and B. Here, I can deal with some more cases. So we have a small example. This is the probability that the additional rule for, in this case, mutually exclusive events. So those are mutually exclusive. So select your card from my standard deck, find the probability that the card is a 4 or an ace. Of course, a 4 cannot be an ace. So, so we have 4 fours, 4 over 52, and we have 4 aces, 4 over 52. So in a deck, the probability of pulling an ace or a 4 is going to be almost 15%, right? So in this case, so we have the probability of one or the other. So that is the addition rule. In the second case, you roll a die, find the probability of rolling a number less than 3. So number less than 3 is only 1 and 2 in our sample space. So, and the probability of rolling an odd number. So odd numbers is 1, 3, and 5. So the probability of less than 3 is going to be, we have only 2 elements, so it's 2 over 6. The probability of an odd number is going to be 3 over 6, because we have six elements in total, minus the probability of A and B, which is less than 3 and not. So in this case, there is only one element in the union. So we have 2, 6, 3 over 6, and minus 1 over 6. So there is a 66% that you can find a number that is less than 3 and or rolling a number that is an odd number. So we have another example using a table. So, well, that's also very simplistic. So here we have the frequency distribution of this volumes of sales in US dollars, and the number of months in which sales representative reach each sales level during the past 3 years. So these past 3 years, so is the sample size. So we are analyzing 12 months every single year. So we are going to have at least 36 observation. So if I add all the months, I'm gonna see that most of the months are gonna be, well, if I add them, it should be equal to 36. So the question is, if sales pattern continue, so what is the probability that the sales representative will sell between 75 and 99.99 or 100,000 to 124,999? So so A is going to be monthly sales between 75,000 and 99,999. So which is this? We have 7 months where these sales have been recorded. And then we have the month sales between 100 and 124,999. So we have 9 observations in that. So the probability that this month we're going to have this or this is going to be given by the probability of A or B. So we know that these events are mutually exclusive because 75 to 99,999 is not the same as the other numbers. So they are mutually exclusive. So we are gonna add the 2 different probabilities, and the probability of this is gonna be given by 7 divided by the sample size. Remember, this is the formula that we use for the relative frequency. So 7 over 36, and in the second case, it's gonna be 9 over 36. So, so the question is, what is the probability that one or the other will occur? So there is a 44.4%, right? So remember, in this case, we are treating this as mutually exclusive or on mutually exclusive events, and then we are using the addition rule. So we have another example that is also very interesting, and I like it because that uses frequency table or tables, uses contingency tables. That's the proper name. So those numbers, those are called contingency tables. And as I mentioned before, that those contains, like for example, in this case, 2 categories, and in the columns we have 4 categories. So we the most common contingency tables look more or less like this. If you are working with a person in epidemiology, so there are so many things that you can say about this particular table. So let me go back to the example. So in this case, a blood bank catalogs the types of blood, including positive or negative RH factors. So given by donors during the last 5 days, given by donors during the last 5 days. So a donor is selected at random. Find the probability that the donor has a type O or a type A blood. So what do we do? So in this case, a person who is type O cannot be type A or any other type, right? Those types are unique. So therefore they are mutually exclusive. So so that is important because we know that the blood type is something very delicate. Somebody's seeking a transfusion, suddenly he's type A and you put type O, the person is gonna die, right? So that's very important. So in this case, the probability that so let's say that you work in the blood bank and you are with your colleagues and say, what is the probability that the next person who is gonna enter this room is either type O or type A? So, so in this case, we mentioned that this is mutually exclusive. So we are gonna use the additional rule or the addition rule to compute these values. So in this case, how many people in the type O do we have? Well, we have 184. So this 184, we are gonna divide it by the sample size, right? And then we do exactly the same by type A. So type A is gonna be the total number of people is going to be 164 divided by the sample size. So the probability that the person ringing the bell in a few minutes, let's say, is 85% that the person falls within any of these two categories, right? So let's say that, well, that's the point, right? So the complement that you get the type B or type AB is going to be, or the probability that that a person is the other types is going to be the complement, right? So there is a 14.9% that the person who enters is going to be any of these two, right? So so we have these. It's very easy. It's very easy to see that these two are mutually exclusive. So we also have an example for non-mutually exclusive. So find the probability that the donor has a type B blood, so that is or is an Rh negative. So we have the number of Rh negatives, we have the number of Rh positives, but also we have the intersection of those. So what is the probability that a person with type B, so if we want to account for the type B, so we are going to do the total of people with type B, because that's the two categories that we were asked to solve. So the probability that the person entering the room has a type B blood and is Rh negative. So we need to account for the probability of being negative, for the probability of being type B, and the union of these two. So in this case, 8 happens to be here. So so if we have the type B is going to be, once again, 45 over the sample size. Then we have the Rh negative is going to be 65 over the sample size, minus the fact that this is in the middle of our diagrams. So we have 8 people who are type B and they are Rh negative. So after solving this, we have that our probability of having a person type B blood and Rh negative is going to be equal to almost 25%. Okay, so so that was a good example. I did like it, and it's very so helps me understand many things. So what I was saying yesterday, and probably I wasn't very successful. So remember, I was solving this. So this table is here. So I already typed all of them here. So we are going to work on this. So last class we did this, and we are going to see how this table can help us figure out our results. Okay. So we are going to come back to this table in a few more minutes. So let me continue. So those are things that we have already talked about, these contingency tables. So these contingency tables are extremely helpful for epidemiologists or the field of epidemiology. So in many cases, you want to know relationships between two different groups of people and two different conditions. So you can use the 2x2 table. So contingency tables are extremely, extremely important. So let me see if I can find something that helps me a little. So epidemiology contingency table. So so this is the 2x2 table. So as you can see, well, this is, if you are interested in medical research, so you are going to be an economist. I am an economist. I always work a lot with this database. Well, it's a search engine. So any paper that you can think of about diseases or anything related with public health, You're gonna find it here. So it's called PEP, MedPub, PET, PubMed, PUBMED. So if you type PubMed, so you are gonna find this website. So this website is very good, very good. You can find information on anything. For example, COVID-19, which is very recent. So it's very recent. So you can find information, and many of these research use this kind of information, like these contingency tables. So so I was planning to find epidemiology. So basically, it's more or less like this: the number of cases and controls, exposed, unexposed. So if you are following these clinical trials for the COVID vaccine, so very likely they are using something like these contingency tables. So these contingency tables at some point are gonna give you something that is called the odds ratios. So the odds ratios are the probability that the odds that something is going to happen compared to something else. For example, the odds of getting COVID among older adults is 3 times higher than younger people, right? Or dying from that. So that's the kind of things that we can do with these contingency tables. They are very helpful. They are very helpful. And if you happen to work with somebody in epidemiology, you probably will be using something like this. So the table helps in determining conditional probabilities quite easily. The table displays sample values in relation to 2 different variables that might be dependent or contingent on one another. So, so we are going to use one of these. So I was very interested in making sure that you understand that these kind of tables is going to be called contingency tables. So we also, in order to make a representation, I guess that was something that we were talking about at the beginning when we were mentioning the types of probabilities, and we mentioned this. So the sample space can be a list of all possible outcomes that we are doing here, or they can be expressed in a tree diagram or in a Venn diagram, right? So Venn diagrams are very easy to understand. I don't have to spend too much time for this. So sometimes the notation for me is kind of like a little bit annoying. So I like to use more words than symbols. But if you are more formal, of course, you are welcome to use symbols instead of words. So, so in this case, how do we represent the sample space? So we can do it by using 3 diagrams, these 3 diagrams. A tree diagram is a special type of graph used to determine the outcomes of an experiment. It consists of branches that are labeled in either frequencies or probabilities. So tree diagrams can make some probabilities easier to visualize and solve. Some people believe that. I'm not very good with tree diagrams, but you can use them. So this is an example. An urn has 3 red marbles and 8 blue marbles in it. So draw 2 marbles and 1 at the time, this time without replacement from the urn. So without replacement means that you don't pull the first ball back before you select the second marble. So in this case, it shows how the first, the second, and the associated probabilities for this. So as you can see, you have 2 different branches, blue and red. So, and you are choosing one or the other. So if one happens to be blue, so in the second row you have 7, and then you have 3 reds. The opposite occurs in the other one. So as you can see, probabilities are changing every time that you are withdrawing red marbles. So you can capture this in a diagram. I think there was also another nice way a very easy way to So I have another examples of 3 diagrams that are less complicated and more helpful, I guess. Hold on, it should be here. Macroeconomics. No, this is macro, sorry. So if I find it, I will show it to you. So these 3 diagrams are very important because we can expand so the sequence of this event and compute the probabilities. So also we can use Venn diagrams. So this Venn diagram is a picture that represents the outcome of an experiment, and it generally consists of a box that represents the sample space S together with circles or ovals. So the circles or ovals represents the event. So we have example of a Venn diagram. For example, in this case, 40% of students in a local college belong to a club. So this is the people who belong to a club. And then we have 50% of them are, 50% of the students are work part-time. So, so 40% of the students are of the college belong to a club, and 50% work part-time. So this is the part-time, this is the college, but in the middle, so we have 5% of the students work and belong to a club. So we are in the middle of this. So draw a Venn diagram showing the relationship that C belongs to students belong to a club, and PT is students who work part-time. So let me ask a question, and I think the answer would be very, very easy to find. So if I ask, what is the probability of the students belonging to a club? Anybody? Nobody? Everybody? I have in the chat 40%. Very good. It's here, of course. Thank you. Thank you. It's a very simple answer. We know that 40% of them are in the club. So the probability that the person works part-time. Answer? Thank you. I'm assuming it's the same. Oh, Wesley, thank you very much. 50%. So, 50%. So the probability that the person works, the probability that the student belongs to a club and work part-time. Answer? Let's say club and pick. How much is this? Thank you, Terry. Very simple. So the probability, that is the conditional probability. So that is the probability that the person belongs to a club, given that the student works part-time. So we can write this, the probability that the person belongs to the club, given that works part-time. How can I express that? Anybody?
Part-time first, and then part-time as the total, and what we're looking for on top.
Okay. But this is the probability. Okay. How can you write it?
write the total as a denominator.
The total as the denominator, which is 100%, right?
And the probability for C on top.
And the probability of
the college students that belong to a club.
the probability of students belong to a club, 40%? Is that what you mean?
Yeah.
But this is only the person who belongs to a club. But this is the person who belongs to a club given the fact that they work part-time. Let me show you some.
Oh, part-time, so it's gonna be part-time
It's
time.
almost something that what we did here.
Yeah, it's PC times PCT equals.
It's almost like this. So
Yeah.
we have the event A is gonna be, or in this case, is that the person work part-time, and B is that she belongs to a club given that she works part-time. So we are gonna multiply the probability of A times the conditional probability of B. So, so in this case, what we are gonna do here is we're gonna multiply the probability of, sorry. So let me make this, let me make this extremely small so we can see, this is 1. So we can see this, right? So the probability that the students belong to a club given that the probability that the student works. So the probability of work is 50% times the conditional probability. So times that the person works, right? So I computed that in that way and I came up with 20%. So, so the last one is the probability that the students belong to a club or work part-time. So this is the probability of club or part-time, right? So once again, we are gonna use the additional rule because, so those are two events. So probably we can use, so are these mutually exclusive or non-mutually exclusive events? Are these mutually exclusive or non-mutually exclusive events? Yes, thank you. Thank you, Terry. That's exactly the answer. Non-mutually exclusive. So we are gonna do 40% plus 50%, 50% minus the probability of A and B, which is gonna be 5%, right? So this is gonna be 85%. Okay, very good. So so we are gonna proceed with our graph, our Excel file. So we have almost like 20 minutes, which I hope I can maximize as much as I can. So let me make this even smaller because I want the formulas to be handy. So I copy and pasted the formulas at the end. We have the multiplication rule and we have the addition rule. So we can use them when we need it. So in the previous case, we were using, so this is the information that you have in your table. Remember the table I mentioned? In that contingency table, we have table 3.1 describes the distribution of a random sample S of 100 individuals organized by gender, whether they are right or left-handed. So we have 43 males who are right-handed. We have 44 females who are right-handed. On the other side, we have 9 left-handed males and 4 left-handed females. So in order to start with this, so I was mentioning we have this so far, right? So what we have to do is to fill the blanks. So in this case, let me make this a little bit bigger because I need my oh, I made it too big. So I need my AutoSum, right? So I am going to click on the total for right-handed. I am going to use the AutoSum. So I'm going to find the sum of this. I'm going to find the sum of this. I'm going to find, this is the sum of the columns. I'm going to find the sum of the rows. And I'm going to find the sum of the rows. And then at the end, I'm going to find the sum of this. Of course, 87 plus 13 are 100. 52 plus 48 are 100. So either way, I just do the 100%, right? So what I did here, so this is my probability table. So this is the probabilities, So in this case, I'm gonna find some conditional probabilities and some total probabilities. Those total probabilities, I'm gonna be using them. They are very handy. So what I mentioned before in the exercise that you have to do here, the guy does this in 5 seconds. So I was using 10 seconds because I said the probability of right-handed is going to be a right-handed male is going to be the male divided by the sample size, right? And I also said let's put some dollar signs and make sure that each of the cells is going to be divided by the sample size. So in this case, I'm going to say enter. I'm going to drag this to the right. And once I have the males, I'm going to drag this to the bottom and I have the whole thing. So if you say what is the probability that we have a right-handed male, so this is 43. What is the probability that we have a male, like a person enters, what is the probability that it's going to be a male? So what is going to be the probability of a right-handed male? So this is going to be, what is the probability that a left-handed female? So we have a 4%, right? So what is the probability of a left person? Well, those are 13%, so and so forth. So the table that we were building is basically, so can you see these guys? Is this clear for everybody? And I am hoping that the answer is gonna be yes. Yes, okay. So, so in this case, we have these probabilities. We're gonna compute them anyways. So in this case, for example, the definition of the probability of males. So it's gonna be equal to 40 to 87 divided by, sorry. So the probability of males is going to be equal 52 divided by the sample size, right? So basically I have it here. So I have it here. I just can say this is the probability. So if I say the probability of females, I already computed it here. So I'm going to say equal. I'm going to click here and say enter. So if I change anything of here, these probabilities are going to change as well. So the probability of a right, so we have the probability of right. So once again, the probability of right is the number of right-handed divided by the sample size. I already have it here. So this is my probability of right. And my probability of left is going to be this one, right? So here we have these examples. So let me check my notes. I don't do any I don't make any mistake as I usually do. I took note for this and what is this? Okay. So in the second case, so we have the probability of male and right. So that's what it says here, right? So basically, we are gonna, because right and male are, is a conditional probability. So, and this, remember, this is, we are gonna use the multiplication rule. So if we look at the multiplication rule, that's the reason I wanted so if we are using the multiplication rule for dependent events, so we are going to use the probability of A times the probability of B given that they has already occurred. So in this case, we have the probability of A. This is going to be probability of A, probability of A times the probability that the person is right-handed, given that is a man, right? So what we're gonna do here is gonna be the following. We are gonna multiply the probability of men, which is 52, times, so in this case, because this is a conditional probability, I'm gonna use the number of right males. So this is gonna be the number of right-handed males divided by the right hand, right? So I'm gonna do 43 divided by 37. Okay? So that's what I'm gonna do. So I'm gonna copy this formula, control copy, and that's what I'm gonna do here. Control B, okay? So is that the, yeah. So so hold on, what did I do here? So let me leave this for the end. So I think I did some.
It was different, the answer in the book, Professor.
Yeah, that's what I noticed. So this is the probability of right and men. So I think I made the wrong notes because I was using, so how can we solve this? So this is gonna be the probability of A, which is gonna be 52% times what is the conditional probability of right and male, which is this one, right?
Should be just this one divided by 100.
No, if we divide it by 100,
it's male and right hand both condition. It's gonna be 43 divided by 100.
Hold on, let me see. Multiply it by this. It's not the one that. Ay, Dios mío, I think I made a little mistake here. So let me correct this. I guess I'm gonna send a second file tonight. So I'm kind of disappointed because I did it for the first time and I got the right results, and then I realized that they are not the right results. So let me go back to the table. I will get back to you later and with a much better explanation. So so far, sorry, so in this case, so in this case, so we have here the, yeah. So so here we have the probability of right and male. So I think you were right. We are gonna divide the 43 by the 100. That's absolutely right. I apologize. So yeah, so we have the number of males who are right-handed, right? So, and happens to be 43. So in the second, we have the number of females and left. So the number of females and left are 4%. So yeah, so we are gonna use the number of people who are, so we already have it here. So that's what we computed in our probability. So this is the person is left-handed and female. So then probably we don't have to do anything else. So the person is a male or a female. So in this case, we have because we are using or, we have the addition rule. So we are gonna do the probability of male and the probability of female. So in this case, we have the probability of males and we have the probability of females. So in this case, we're gonna do this plus this, right? So the probability of females or left, right? So in this case, we're gonna do the probability, so that is a mutually exclusive event. So so
it's gonna be 52 plus 87 minus 43, all divided by 100.
all divided by. So in this case, so we can use these percentages, right? So this is the probability of male, right?
Yes,
Plus the probability of right.
Right. Minus the right plus male.
Minus
the right plus male, because we need to, yeah.
Sorry. Yeah. So this is the probability of males, the probability of right-handed minus the probability of males that are right-handed. So 96%. So we also have, sorry for this. So that is easy. I mean, I was trying to do it. I think this guy gives a better way to do it. So, but it's very clear from the table. So, so we have the probability of female or left. So we have then we have the probability of females minus the probability of left, sorry, plus the probability of left minus the intersection, right? So 0.57. So we also have the probability of the complements of males. So that is going to be equal to 1 minus the probability of males. So the conditional probability of right-handed, given that the person is a male. So I think here we have the probability. So basically speaking, we're gonna see the probability that the person is a right-handed, given that the person is a male. So we're gonna divide the 43 by the 52. So here the question is the probability that the person is a right-handed, given that is a male. So we are gonna do 43 divided by 52. Equal 43 divided by 52. And then we have, let me make this smaller. So also we have, so the probability of a female, given that the person is left-handed. So this is the probability of a female. So this is the probability of a female given that the person is left-handed. So we need the probability of female, so this is the probability of female given that she is left-handed. So we have 4/13. So the person is left-handed and happens to be a woman. So it's gonna be 4/13. And the next one is the opposite. So that's the conditional probability that is the opposite. So we want the probability that the person is left-handed given that she's a woman. So in this case, so that's the conditional probability. So in this case, we have the number of left-handed women among all the women, right? So we are gonna do, so this is the left-handed woman and this is the number of women. So we are gonna divide 4 by the number of women, right? So those are the results. So as I said before, I want to see formulas. I don't want to see typing the numbers. You are seeing the numbers. So I want you to understand what we are doing. So in this case, this table is extremely helpful. So those are some of the probabilities that we built before. So, so we can use them as, so here we also have this, you can fill out these blanks and answer the probability that the person stretches. So of course is the total of stretches by as the sample size, the probability of stretching having that the person has no injury, and the opposite, the probability that the person has no injury given that she stretches. Okay, so is there any questions so far? I'm sorry for the little confusion at the beginning, but I'm gonna revise the formula that I had and make a note on the side, okay? So any question? No? Was a boring class? Well, I shouldn't ask that question because I will be afraid of the answer. So any question, guys?
Professor,
Yes.
it's about the homework for turn 23. Is included this class, the homework for Excel?
Well, what you have to do, so the goal of Excel, once again, is that you do what I did, right? So it's very easy. If you are looking at your Excel file, and you see that I divided here, I want to see that formula. So, and more than seeing the formula, I want you to understand what is these two elements.
Okay,
So
but the homework is included in this class. That's the...
Yes.
Okay.
Sorry. So
okay, no problem.
As I mentioned before, thank you for reminding me. So you have a previous file, right? This is the class stats2. So let me, no, that's not the one. So let me, we had a file from the previous chapter 3, it should be chapter 3. So let me open economics class. That's materials. That's what upsets me. When I am looking for something, I don't find it. So you remember the file that I sent you before? So let me go to Blackboard. Let me go to Blackboard. Let me go to Blackboard. So chapter 2, you have to use this file, right? I hope you are doing that. So you work on these assignments, right? You have to create all these things. So how should you proceed? Well, now you have many spreadsheets at the bottom. what I want you to do is to copy all these. I mean, there might be a better way to do it, but that's the only way I know. So you copy and you paste it in the previous. Open one of these spreadsheets and then paste, right? So that is one of the files. Remember, it has two different files, two different spreadsheets. So if you click here, it's going to open other things. What I do is I go to the other side, I highlight all my information, then copy, and then paste it in another in the previous. So you have only one file, right? So now you can solve this. I mean, you can forget this one and work only in one file, right? So when you submit, you can even change the title. Let's say De La Cruz module 1, and then so that's what you are going to submit to me. Okay, is that clear, Dennis?
Yes, Professor.
Okay, so so that is going to be very simple. I don't have to be opening multiple. So remember, you are a class of 30 students almost. I have a class of 100 students, and I have another class of 30 students, and I have another class of 30 more students. So it's a lot of students when you count the numbers. So when you submit your work, please be mindful that the simpler, the better. You are going to make my life easier. I will be able to focus my attention on assignments as they go. So please try to comply with this, okay? So any other question? Let me stop the recording. So I don't want to record that I am scolding you guys.